Well, hello. Welcome, everyone. This is going to be really fun. This is going to be a stream talking about how I did some simulations for the Is This the End of Astronomy video. It's been a while since I've done a stream, so this is going to be a good time. Let me know in the chat if you can hear me, where you're joining from, and feel free to, throughout the duration of this, just like leave questions and comments and whatever in the chat, and I'd love to take some questions, particularly at the end, and show you guys this cool thing that I made over the course of the last year. It kind of, well, yeah, let's just dive right into it. I have a couple of slides that I'm going to use just to sort of like anchor things and talk you through it a little bit. But mostly I just want to play around and show you guys what I've been working on and how I was able to simulate 42,000 Starlink satellites, and not just like, ooh, it's a pretty animation, like, it's just some animator putting a bunch of dots around and pretending that it's realistic. This is like the best simulation I've been able to find. Well, the one that I created is the best animation that I think exists to show what these satellites will actually look like to the human eye, to cameras, and stuff like that. So, hello, Tommy. Hello to my mom, Elmarie. Okay, good to hear that the audio is rolling good. So yeah, let's dive right into it. Give me one moment. So we've got a cool little slideshow to walk through. So I'm going to kind of treat this like a class. So we're going to sort of go slide by slide and talk a little bit about the things, and I might wait a little bit to get your questions in and answer some questions. So let's dive straight into it. So how to simulate 42,000 Starlink satellites. Oh, wrong keyboard. I have two keyboards here and it's going to be confusing. So this is what we're talking about. This is the simulation I created that you can watch in Is This the End of Astronomy video that I put out in about a month ago, I want to say. Also, happy full moon. I believe I released that video on the half moon, and so now it's full moon and we're back on a full moon, new moon release cycle, hopefully. But yeah, so this is the kind of thing that that didn't exist a year ago, that I was wondering, what are Starlink satellites actually going to look like? And I couldn't seem to get a straight answer of a visual representation of it. So we're going to dive straight into this simulation and how it was built in this stream. And in case you missed it, in that main video, if you look in the corner, the bottom left corner of every single one of these simulations, I took some time in the final stages of the project to add a little caption that tells you exactly what we're seeing here, what's being emitted to show the point, like what parts of the simulation are being exaggerated just so that you get the point across, or that I could get the point across, or like, are all the things turned on so that it's the most accurate representation possible. So yeah, if you look at any of those simulation shots in the bottom left corner, I doubt anybody noticed this because it's super dim. And in fact, you kind of have to like do an exposure boost on it in order to see what it says. But so this shot, the one we were just watching, is all phases of Starlink. So we'll talk about a bit about what that means in a bit. Seen from Cerro Pachon in December. So Cerro Pachon is the mountaintop where the Vera Rubin Observatory will be located. So that's the location on the Earth. And Starlink is really sensitive to the location on the Earth. Like, where are you and what season is it? And we'll see why in a second. All that didn't really make sense to me when I started this project. I was just like, how could it be so different to see, like a ton of Starlinks in one place in the summer and nothing all night in the winter somewhere else? Like, that doesn't make intuitive sense. So I'll try and get across an understanding of how that works in this stream. So yeah, and then there's atmospheric extinction and Starlink's reflectance represented in this shot, and we'll talk about what I mean by that as well. We're also seeing the magnitudes of VisorSat satellites. So there's sort of, we'll go into that in a bit more, and 30-second exposures per frame. So let me go back. So what we're seeing here, each frame is 30 seconds of time passing, and the shutter is being held open for 30 seconds. So it's essentially modeling what a camera like this one would actually see if I set this to a 30-second exposure, right? And let me turn the ISO way down so that I don't burn out my sensor. And I'm going to take a 30-second exposure of you guys. Here we go. Let's see. 2, 3, 4. I don't know. Should we wait here for 30 seconds? We'll continue, and when we hear it go, then we'll know we'll know how long 30 seconds is. Okay. So, big question that I want to address about this. Okay, I'm too distracted. Let's just wait for the 30 seconds. I'm gonna guess now. No? Now. There we go. 30 seconds is always way longer than you think it is. So here I've taken a photo, and it's just pure white. I should switch screen. I'm not going to take the time to switch screens, but it's pure white because it's daylight, and it just let in like so many photons for 30 seconds. But in the middle of the night, right, it's really dark, obviously. So if you take in 30 seconds of light, you get a picture like this one, which is substantial. Okay. Anyway, let me turn that off. Okay. So why? About a year ago, I was really confused. I was thinking of making this video about Starlink. I wasn't sure whether it was a strong topic or not, if people would be interested. Wasn't sure if it's even a big deal. And the more I learned about it, the more I got confused, because on the one hand, a lot of people who are really excited about Starlink were talking very loudly about, oh, this isn't a problem, like you can't see them at all, it's fine, like all of these astronomers are kind of overblowing things, right? Like overblowing the impact it's going to have. And at the same time, all the astronomers, particularly on a place like Twitter, which is basically like a screaming match, they were all saying like, this is not a good thing. This is going to cause major issues for astronomy. And so I was sort of caught in between, like, how do I think about this? And so to give you some context, like where I'm coming from is, on one hand, I'm a person who has always been transfixed by the night sky. I mean, this channel, this series probably will get that across if you've seen my other videos. But on the other hand, like, I'm a huge fan of SpaceX. I'm a huge fan of JPL and all the efforts to like bring humanity beyond Earth. I think it's kind of like one of the most inspiring things that we're doing as a species. It's just like when we are able to like land a freaking rover on another planet like Mars, and we're about to fly a helicopter, or attempt to fly a helicopter on Mars for the first flight of anything on another planet. Like, that is just so ridiculously insane, and it fills me with such hope, because if we can do that, then like we can do so much when we work together. So anyway, so on one hand, I get really inspired by space feats, and I was really excited about Starlink when I first heard about it, and I was like, man, this is going to be a huge deal. And I'm still excited about it. I think it's still going to be a huge deal. And on the other hand, it's like, oh man, if this is going to like ruin the night sky for like not just me and not just thousands and thousands of other people, but like my descendants and my great grandkids, if they're not even going to know what a night sky is, like, this catches my attention. So this is where I was coming from about a year ago. Like, is this going to destroy the night sky forever? And the short answer, well, actually, I'm not going to give you a short answer. That's what this whole thing is about. So let's dive into that and see where we lead on that. So I started looking into simulations, and this one was released about a year ago. I think it was March 15th of 2020. So, but this is like not a very clear representation of what's going on. This is very like engineering. It's really accurate. It's beautiful simulation, but unless you know what you're looking at, this is not accessible to anyone. But this was where I started to realize, like, oh, okay, this actually could be an issue, but I'm still not sure, because if you look at all if you look at this top left graph, this is essentially what a viewer's eyes would see looking at the horizon. And the orange dots are really bright, like magnitudes less than 5. And so you can see that all night, and this is as time goes by, as the Earth rotates, you can see that a lot of satellites are visible. A lot of satellites are visible even in the middle of the night, which is something that it was a misconception on my end of like, these satellites aren't going to be visible in the middle of the night, right? Because they're only visible when light is shining on them and reflecting down. Sunlight is shining on them and reflecting down to the Earth. So if they're in the shadow of the Earth, like, it's not going to be a problem. But as we'll see, it is still a problem, particularly in the summer. The other simulations that exist are not even remotely having to do with astronomy. It's just sort of like showing this is what 42,000 satellites will look like, the sheer number of it. But it doesn't give you a sense of visual scale, like, will I be able to see these? Okay. And again, welcome everybody. There's a lot of people here. So thank you for joining. And if you have any questions as we go along, feel free to leave them in the comments. I've got a comment chat, or not the comments, but the chat. I've got the chat going here, and I'll try and answer questions that come up. Okay, so to answer this question, I drew on some code that I'd written a long time ago, back in 2018 at the start of the Verse project. I wrote this code to simulate basically the moon and the Earth, and just to get their positions and rotations in space, and sort of render them to scale. The very first episode on this channel, the Moon episode 1, that was rendered. A lot of the Earth and Moon shots there were rendered in this program called VerseView that I created. So it's a custom visualization code, so I can basically do whatever I want with it, given enough time. It's made in Python, the GLSL language, which is very like standard, a very standard graphical language to like render things, and also the Qt language, which is sort of like it's a Qt framework. So it's a way of rendering graphical user interfaces. And it's also built on this package called VisPy in Python, which is an awesome visualization package. And they did a lot of work to like make it fast from Python to talk to really like hard-hitting graphical framework stuff like OpenGL. And so this code, VerseView, basically just uses the VisPy GL API to like say, hey, computer, I want to draw a line, or I want to, in this picture here that we're seeing, we see the Earth in the middle and the moon is on the left and the sun is on the right. And there's all these dots, and these dots are showing the lunar spring tides. So basically, my program, VerseView, says I want a dot here in 3D space, and the Earth should be here in 3D space, and the moon should be here in 3D space. Okay. Then we send a message to GL, which is the graphical language, and GL gets a message saying, hey, render all these things at these positions. And so it does a bunch of matrix math and stuff, and then it basically spits that out onto the screen, and then we save those frames as PNGs and PNG sequences, and then we have a movie. So this is basically what VerseView does. It also does a lot of keyframing and interpolation for cameras and objects. So, if you have a cinematic scene, you want to have camera moves, right? And you want to have, pan in and pan out, or track in, track out, and pan left, pan right. And that kind of thing can look really janky if you don't have nice keyframing and nice interpolation math. So VerseView also implements a lot of really nice interpolation, and we'll see that in a bit. I'm going to give you some demos of this. And then finally, just high quality rendering. Like we need this is a lot of technical language, but we need like multi-sampling, which is, I don't just want like jagged edges rendered for every pixel. I want to like render a frame that's larger than the real frame and then sample it down so that it's like smoother on edges and stuff. Yeah, so that's what VerseView does. And then there's VerseView Planetarium. I see some questions from Tommy, and welcome Dutch Ellie. Yeah, indeed, Ellie, I went crazy on this algorithm, and I'm very excited to show you more. Greetings from Germany. Hello, Spacebird. Welcome. Let's see here. It's possible to calculate how many satellites will be in one frame with 42,000 satellites. I know it depends on the focal length, but it will be a fun thing to know. Yeah, so that's actually a really good question. And I think the best way to answer that is to show you. So we'll get to that very, very shortly. I'm wondering about radio and microwave astronomy. Have you looked at that from Matthew Malacher? I didn't do any like direct analysis of radio frequency astronomy or microwave astronomy with my simulation code. But you can think about the address, like the area that a Starlink satellite can reach below it as the area of impact for radio astronomy. Like if there's a Starlink satellite flying right over the head of, right over the top of a radio frequency dish or radio astronomy dish, and it's blasting internet down to the masses. In some cases, that radio dish can actually, the receiver on it can actually like literally melt, literally like short out because there's so much radio frequency energy going into it. This is just something that blew my mind as I was learning about that. Now, again, so in a second, we'll see what kind of altitudes are these satellites flying at, and like what kind of area can they address for a single satellite. So that'll give you a sense of like the magnitude of the radio impact. Okay, so let's continue. So VerseView Planetarium, a year ago, I really seriously dived into this. I took the VerseView code and I generalized it and then extended it to render basically the solar system. So I'm using VerseView to render the solar system. So at this point, we have sort of VerseView Planetarium sitting on top of VerseView, and on top of VerseView, or below VerseView, you have VisPy, and then below VisPy, you have GL. Okay, so that's the whole idea. And the reason that I wanted to do this in Python, by the way, is because Python is like the language of astronomy. So for instance, yeah, and eventually we want to render the universe in this thing. That'll be fun. The JPL ephemerides, I don't know if I'm saying that right. I always feel like I'm saying it wrong. The ephemerides, which are basically like, where are these objects? Where is the moon in space right now? Like this very second. Give me like XYZ coordinates relative to the Earth in some reference system, right? Like what are the positions and rotations of every object in the solar system? That's called ephemerides, and JPL provides a really accurate ephemerides. It's mostly for their like missions to Mars and the moon, and all of their missions around the solar system. They need to know very precisely where are the planets so they can plan for gravity assists and all that. So Python has a really great package for this. It's just literally called JPL-FM, and it's standard use in astronomy circles. So this is a big reason why I wanted to use Python for all this, because Python is the programming language of astronomy, unless you're doing really like high computational resource stuff like smooth particle hydrodynamic simulations. Then you really need to like have a dedicated C++ code to do that heavy lifting. But in general, like Python is used frequently for this kind of stuff. Something that I want to show you actually is a great video. Oh boy, that's quite a vibe. Here, I'll open it on here. A great video by our friend, Dr. Becky. So let's go to Dr. Becky's channel. So Dr. Becky, of course, is the one in the video who kicks off the Is This the End of Astronomy video, and she has a fantastic channel. Definitely go check it out. But there's a video in here in particular about how I use code as an astrophysicist. So she literally like goes through all of her main uses of Python as an astronomer, as an astrophysicist. So that's very cool. So definitely go check that out if you're curious more about the use cases of Python in astronomy. Okay, so anyway, VerseView Planetarium is this code built on VerseView to simulate the solar system. I saw we had a couple of questions. Let me get to the end of this slide and then I'll answer some of your questions. So yeah, the main focus of this program is on the Earth-Moon system. And so what do I mean by that? I rendered the Earth's atmosphere at the best accuracy that I could get within my time constraints, and we'll see in a moment. And also some 8K textures for Earth, as well as 16K, and I think in one case 24K texture. So this requires a lot of GPU RAM, but it really makes for a nice product. So you'll see that shortly. Okay, so let me answer one or two of your questions here. So I see. Yeah, Dutch Ellie, the graphics coding is a beast. It's Dutch Ellie is asking about or saying that they have such little motivation to get into graphics coding, and honestly, it's a beast. It's a heck of a topic, and it's very confusing. But hopefully, I can give you a little bit of an overview if you do want to start in the rest of the stream. So. Let's see, with WebGL, you can easily plot 50,000 objects in any space. Haven't worked with Python yet, but I'm quite confident it can as well. Yeah, so Python itself can't really render anything. I mean, sort of. There are some packages there's this one called Turtle, which is a classic, and it can render things directly from Python. But it's kind of a slow language, so it in general can't do like really fast processing, like, oh, I need to see a new frame every 60th of a second, right? Python is going to struggle with that kind of thing. So this is why we use things like GL, and good point about WebGL. In fact, more on that later. I mean, actually, I'll just say now, I mean, like, I would love to make what I'm about to show you a WebGL thing, but I just don't have the time right now to transfer it. One thing I wanted to mention about VerseView Planetarium is that it was used in this Veritasium video called "These Are the Asteroids to Worry About." So I needed to render this asteroid Duende, and I was like, well, I've got its precise orbital parameters, like, you know, what is its orbital curve, and I want to show that accurately. Well, you know what? Let's just use VerseView Planetarium because it's built for that. It's built for using astronomical data sets. So anyway, so I thought that was a cool thing to point out. Okay. Okay, so here's where we really dive into the fun stuff and the technical stuff. I'm also going to try and keep this under an hour, at least until questions. So let me know if I'm going too fast or, if I'm going too slow. So step one to simulating Starlink is understanding the orbital shells. So Starlink is going to be launched in a bunch of shells, as we saw in the main video. Let me pull that up just to sort of point at it. One moment. Let's go here. I'm gonna switch to, oh boy. There we go. Hey, look, that's us. That's pretty meta. Okay, so is this the end of astronomy? Here we are, right? So let's go to the part where I'm showing the shells. This is just a little easier to show in the render than to launch the program. There we go. Okay, so there's a bunch of shells of Starlink satellites. The idea is let's launch a whole bunch at low altitude, and then let's launch a whole bunch at slightly higher altitude, and then keep going, basically. And SpaceX have acknowledged that launching satellites at higher altitudes is worse, which we'll get to shortly. But this simulation code is based on essentially the initial orbital parameters that they published. They haven't really, or they didn't publish it, that the FCC has published about what they've requested. So essentially this is the best guess of like what their final plan is for 42,000 satellites. But internally within SpaceX, this might have changed already. So, but I don't have access to that information. So it does kind of look like an atom's electrons with more defined locations. That's a very interesting point. This would be a very weird atom, though. And I think the protons and neutrons would be really, really tiny instead of like the Earth being this huge thing and the electrons going around it. I think, isn't the space between the proton and the electrons like just absolutely massive in comparison to the sizes of them? I feel like that's how that works. Anyway, let's actually peer into the code. If you're intimidated by code, don't worry. I'm going to try and simplify, or not just simplify, but like give you context for things to my best ability. So let's open up one of the Starlink renders here. And in fact, maybe I should just duplicate this so that I'm going to show you a specific, we're going to make our own Starlink rendering here. Hold on. There we go. I'm using a sort of weird double screen capture situation here. Let's see. Does this work? And please let me know if I'm pointing at something that's actually going off the screen, or like under my head in the corner. Okay, so let's pop this over here. So here's basically a program, a shot in VerseView. This is how it works. So we have a bunch of imports here, which is basically just like, give me the resources so that I can do the job. So you don't need to worry about those too much. And this is really where the main stuff happens. So we give this particular shot a name. So I'm going to call it Night Sky Starlink 63. There are a lot of Starlink renders that didn't end up in the main video. And I'm planning to make a full like concatenation of them in another video, which will be a fun one. Here we have what phase of Starlink deployment are we at. So phase 1 is the one that they're deploying right now. Phase 2 is the one that they'll probably deploy in about 10 years or so. And phase 3 is somewhere in like the 20 to 30 year range of deployment. So if we scroll down, just skip some of this real quick. Because we're talking about orbital shells, let's just focus on this. So this code right here. So what the heck are we looking at? This is 3 lists, one after another, about that describe what the orbital parameters of each Starlink shell will be. So for instance, let's take this first one. So this shell is shell 1 at 550 kilometers, 72 planes by 22 satellites, all at 53 degrees of inclination. I don't know what your background is going to be coming to this. If you've ever played Kerbal Space Program, this inclination is literally your orbital inclination. So if you haven't played that and you don't know what I'm talking about, I'll show you in a moment. And then, so basically I just encode this information into a tuple, which is this little like parenthesis thing. So the altitude, 550 kilometers, the inclination, 53 degrees, the number of planes is 72, and the number of satellites in that plane is 22. So to actually show you what this is doing, I'm going to quickly comment out all of this code right here. And I'm going to set this to phase 1 because I'd only want to see phase 1. So what I'm doing is I just want to see phase 1, this list of Starlink shells, and I only want to see this shell, just to show you what one shell looks like. And then let me just make sure this isn't going to like break my computer. So this is us instantiating the Starlink objects. I'm also going to make them particularly bright, like extra bright, because I want you to be able to see them. Texture, let's do the final orbit Starlink. Okay, great. And I think that's kind of it. Let's just give it a launch and see if it crashes. Mostly I'm just wondering, when it draws the circles for what their orbits are supposed to look like, it kind of takes a lot of computing resources. So I just want to make sure that that's either off or, yeah, no, I think it's perfect. Okay, great. So let's launch this. I have a demo running here of VerseView. We'll come back to the demo. So let me show you what one orbital shell looks like. So I believe that's going to be, yeah, it's this one. So here I am, I'm in a terminal, in a shell, and we're just going to launch Night Sky Starlink 63.py. Okay, for non-coders, comment out means that part of the code is ignored. Yes, thank you for that, Angelo Michael? It's either Angelo Michael or Angelo Mikel, depending on or something else, depending on where you are in the world. Okay, so looks like we've got a weird situation. Okay, yeah. So welcome to VerseView. Here we have a bunch of selectors on the left, which let us go various places around the solar system. So I'm going to go to Earth because I like Earth. I think Earth is great. And it takes a moment because it's calculating where the planets are and where to put me in it. And hey, there we are. So there's the Earth. It's looking good. Let me speed up the camera a little bit here. And we can see some dots floating around, which is kind of interesting. You might think, wow, those look like Starlinks, and you'd be right. So let's see here. I've also seemed to have turned off the, so I made these extra bright. So this is not accurate, by the way. The brightnesses of these Starlink satellites is very non-accurate. They are not brighter than the Earth is in direct sunlight. So I can change the exposure in the program, I can change the contrast and the offset as well, but I'm gonna just sort of bring it down a little so you can see the Earth. So here we are flying around. So this is what Shell 1 looks like. So there's 72 orbital planes here. I believe time is kind of going in real time here. Let me just see. Are they moving at all? Well, they're moving, but they're moving very slowly because this is their actual orbital velocity. So based on their altitude above the Earth, you can calculate for a circular orbit what their orbital velocity will be. And so this is the accurate orbital velocity that they would be moving at in real time. So there we got some Starlink dots. And if the Starlink dots are incredibly hard to see, please let me know. I can do some things about that. But yeah, so this is what 72 orbital planes look like with 55 satellites each. So that's Shell 1. Now I hope that the whole plane and number of satellites in a plane doesn't confuse you. So let's just make a custom configuration of a shell just to show you what I mean by all these parameters. Whoopsies. So let's see. So we're going to do 550. We'll make it 45 degrees inclination just for simplicity's sake. And then let's make one plane and we'll make like 100 satellites, okay? So let's try this out. For the C and C++ people, it's kind of nice in Python. Any number is identified automatically as a float. So this originally was, I think, 1.0 maybe. And so you don't need to worry about types as much in Python, which is great. Okay, so let's launch that up. And voila, I forgot to save the camera's location. So let me fly back to Earth. Oh, whoops, I just went to Neptune. Let's go to Earth, please. Okay, there's the Earth again. I'm gonna save the camera's position this time. I swear. I'm gonna remember. Let's see here. Okay, so let's interpret what's going on here. First of all, let's find the equator. This is the Earth, and I don't know exactly where the equator is. But there's America, and Mexico, and North America, and Canada, and Cuba, and there's South America. And so I know that the equator is like kind of in here somewhere, right? So this is the first thing I wanted to show you is this is one orbital plane with 100 satellites in it. So there are 100 satellites in a circle, and you can see that it's not exactly level with the equator. In fact, it's off the equator by 45 degrees, also known as its inclination. So that's how that works, basically. Voila. And these positions of the Starlink satellites are for the people who are interested. They're being updated inside of the shader code. So basically I implemented Orbital Dynamics, very simple Orbital Dynamics in this case, within the GLSL shader. So basically we rotate the satellites on the GPU rather than rotating 42,000 satellites on CPU, which would, melt your computer, or at least make it render very slowly. Okay, so that's what one plane, one shell, one plane looks like. But let's just go full out now. I'm gonna re-instantiate all this. Uh-oh, I've made an error there. Okay, we're commenting out the comments. And so now we have all of phase 1. Let's look at all of phase 1. So we're still in phase 1. Let's just go ahead and launch it. And again, I forgot to save the camera position, but that's okay. Okay, so got some comments. Let's see. Satellites are visible to us, assuming people have a stable high. Okay, that's great. Great to hear that the satellites are visible. Please, if anybody is like, what are you talking about? I don't see any satellites. Please do let me know. Okay, so great to hear. Okay, I don't exactly remember. Awesome. Thank you guys. I'm glad to hear that this is making sense, even if I'm sort of winging it. Okay, so this is what all of shell or phase 1 with all of its shells will, in terms of the number of satellites, what it'll look like. So this is sort of the phase 1 of making a Starlink simulation. You put all the satellites in their accurate positions, and you make them rotate around the Earth at the right orbital velocity, and that's about it. So now what? So the next thing that we need to do is step 2. I don't know, this is kind of overdone, but step 2 is, and actually I should have added one more thing here, reflectance mapping, but also it's about rendering the extinction, the atmospheric extinction of the satellites. So I'll show you what I mean by both of those things. If you remember from the previous slide, in here we had two things, atmospheric extinction plus Starlink reflectance. So let's take a look. Oh boy. Okay, maybe I'll just, okay, come on Keynote. We can, I don't need the animations. I just need to go back. Okay, forget that. I'm just going to show you what I'm talking about. So the first thing we need is, do you see how the satellites, as they pass into the Earth's shadow, they disappear? Or if they're coming out of the Earth's shadow, they reappear. I should speed up time so that this is more evident. So let's make time 100 seconds per second, I guess. So 100 times faster. I think I forgot to save the camera position again. Okay, well there we have a swarm of Starlinks, which is rather cool. It's a good point that if we're watching this on mobile, it might not be so visible. But maybe if they're in motion, it'll be a little bit more visible. I mean, it looks like a bunch of flies just like swarming the Earth. But this is what this would look like at 100x speed, right? And you can see the Earth rotating down below it. Okay, so let me set the camera position and save it. So I'm at F1 to save the camera position. So there we go. And so as they pass into the Earth's shadow, they disappear, but not very accurately. Like there's issues here, because as a satellite passes into the Earth's shadow, it actually passes through sunset. So if you imagine, have you ever seen a video from the International Space Station of it going into sunset? Imagine we're on the International Space Station, or we're a Starlink satellite, and we're slowly passing into the Earth's shadow here. As we pass through, our spacecraft, or our eyes, are just going to start seeing more and more red light, because that's how sunsets work, right? And so in theory, like, all the light hitting us should just be redder and redder until it passes into the shadow of the Earth. So that's what I decided to simulate first. So I'm going to go ahead and turn that on. Okay, so actually it already is on, but they're just so bright you can't see it. So let's make them darker. I think this might be able to show the effect of it. And I'm going to quickly turn reflectance off just so that we can understand what's going on. Okay, let's see. Awesome, awesome. Okay. Okay, it's still a little, oh, okay, we can start to see it a little bit here. So if I fly down into the Starlinks a little bit, maybe time is now too fast. Give me 1 second, I'm gonna slow time down by 10x. So there's 10 times. And now we wait for a moment. One of the things that sucks about having this in Python is that it takes a little while to launch up. But honestly, if it was in C++, it would probably take ages to compile anyways. Okay, so if we look at some of these satellites now, as they pass into the Earth's shadow, they start to get redder and redder until they vanish. If you've ever watched the ISS fly over, you see this happening. Just as it inches into the shadow of the Earth, it gets redder and redder until it's completely gone. And so, yeah, so this is how that works. And this is actually using the same code as this atmosphere is. So I literally just like took the code from the Earth's atmosphere and I stuck it on each Starlink satellite is running the entire atmosphere code. And it's saying, pretend that I am a camera. The Starlink satellite is a camera and it's viewing the Earth from a particular vantage point. Like say, you know, at the Starlink satellite's orbit position. And then calculate what would be my color if light rays passed through the atmosphere and then on to me. What would be the atmospheric extinction? And so there we have it. I think it looks beautiful. You can see them, you know, coming in and out. Anyway, that's enough about atmospheric extinction. I'm going to quickly make the Starlink satellites a bit bigger because I'm a little worried about people on mobile or people with slower internet connections. So let's go ahead and just bump it up by maybe that'll do it. Let's try that. Okay. If they get too big, they just start to look really weird. So hopefully this is not too big. So then once you have, there we go. I think that'll be a lot more obvious. Once we have these satellites coming in and out of the Earth's shadow, something else that I realized is that, how can I show this? Let me grab here we go. I'm gonna grab this little satellite model. So let me switch to full camera view. Here we go. Okay, so if we imagine that this little Lego creation is a Starlink satellite, right? As the light from outside hits it at different angles, it illuminates more or less, right? So like at that angle, you can see a glint happening on this top part, right? Let me bring it even closer. Thank you, autofocus. So you can see it, you know, it glimmers. And then in some angles, it's a lot darker, like there, right? If I move it around at every different angle, it kind of has a different look. So that kind of, you know, difference in reflection based on where the angle is that you're looking at the satellite, that I just term that reflectance. I feel like there might be a fancy term about it, but reflectance seems to make sense to me. Let me set this down. So the next step in showing a Starlink satellite accurately is to model the reflectance of the satellite. There is somebody driving very loudly outside. And to measure the reflectance of the satellite, I kind of had a novel approach that I don't think anybody else has thought of or has done. But I think it turned out really well, and you'll see that shortly. So let me show you what that technique is. Okay, here we go. So let me swap back here. Let's pop out of here. And I want to show you a series of renderings that I did. So we go to, let's go to the F drive. And then I believe it's in frames. Give me a moment while I find it. I should have pulled this up earlier, but that's okay. So, so there's sort of two configurations of Starlink satellites. One of them is when the solar panel is up and it's in its final orbital configuration. Maybe I should show this with the Lego. I'm not sure. I think it's okay. I think I show it in the main video anyways. But when the panel is up, you know what? Actually, let's just watch the video because that's going to be better than hand explanations. Here we go. Okay, so when the panel is up, this is the sort of normal operating phase, how it looks. Whereas when they're doing orbit rays, they lower down the solar panel so that it's basically in line with the thrust vector of the ion thruster. And the reason you do that is so that this giant solar panel doesn't cause the spacecraft to torque out of control. I mean, there's these attitude control, what's it called? Control motion gyroscopes? Control wheel gyroscopes. And they control the attitude of the spacecraft, but they can only do it so much and so quickly. And my guess is that the ion thruster will just make the satellite tumble if it doesn't have its panel down. So with the panel down, the problem is it reflects sunlight way more. So let's go forward a bit to this shot, right? That shot. So you can kind of see that. This is with the panel down, and even though they're passing into sunset, or they're passing into the Earth's shadow, that's the point where they're going to be the brightest because the panel is down and the light is going to just bounce right off of it straight down to the ground. So to model that, I did two things. Firstly, and let's go back here, I just modeled I took the 3D model, this exact 3D model of the Starlink satellite, and I put it in the Unreal Engine where I did a lot of these renders, okay? And then I rendered out literally thousands, if not tens of thousands, of different positions flying around the spacecraft. So here you can't even see it, right? Because the light is not hitting at an angle where it's visible. But as we fly around, I kept changing the sunlight angle and I kept changing the camera angle. And I did a bunch of these fly-arounds in a very predictable way so that I could know exactly what the camera angle was at any one of these frames and exactly what the sun angle was at any of these frames, okay? Why do I need to do that? Well, that leads us to, let's go to the lookup tables. That leads us to, I believe it's in assets, textures, maybe it's in data, Starlink. Here we go. Okay, great. So flare full scale. Yeah, these are the final ones. So, oh boy, that's a TIFF, and Adam does not like looking at TIFFs apparently. Give me a moment. I'm going to open up the final thing here. So because I knew what the angle was for every single one of those frames, I could calculate what the brightness was of each frame by basically doing a norm on the whole frame. So basically adding up what is the brightness on every single one of these frames. And how does that correlate with the angle that we're looking at it with and the solar angle, like the sun's angle on it. Okay, so this is the final product of that. And so okay, you know what? Actually, I just realized there's probably a better way to show this. Let me pull up, whoopsie. Let me pull up the data analysis thing. This is something that I'm going to make, the following is something I'm going to make available to patrons of the channel. So feel free to go become a patron if you want to read through this in excruciating detail. It's a technical write-up about how I did all of this, basically. Just give me one moment as I find the HTML file. Interesting. Okay, well, we'll just start a Jupyter notebook here then. Or Jupyter Lab, why not? Okay. So basically in Jupyter Notebook, I took, which is a way of using Python, I took all of those frames of thousands and thousands and thousands of angles and sun angles, and I put it into a single code base, basically. let's scroll down here. Okay, there we go. So this is what the solar panel looks like when it's down, and this is what it looks like when it's up, okay? And so when it's down, it reflects light a lot more than if it's up. Okay, great. So this is also, I also did some simulations with the visor sat mitigation that SpaceX did. So this is without it, and this is with it. And you can see what the visor sat does. It actually just it just creates a shadow all across the entire spacecraft, which is a pretty clever design, honestly. But we'll see how clever it is. Let's see here. So, okay, yeah, so here we go. There's the GIF of, you know, every different sun angle and every different camera angle, and taking every single one of those frames, I was able to compute a norm, which is basically just a number about how bright it is. So here's a really bright image. So we have a number here, 317,000 is the norm of this image, which is a way of measuring its brightness, right? So compare that with this darker image, which has a norm of 85,000. So that's a lot less, right? And so the norm ends up being a really nice way to calculate the average brightness of a frame. Okay, so the idea here with these lookup tables is that along the x-axis, we have the different, now I'm trying to remember which one's which. So, yeah, okay. And then x and y, sorry, I should have remembered this beforehand. So x is the angle of the camera and y is the angle of the sun. Okay, right. So if we look at this table closer up, as we go along the x-axis of pixels is representing different camera angles that we're looking at the Starlink satellite with. And then the vertical axis, the vertical axis here is looking at the different sun angles. So it's kind of hard to get your head wrapped around, but I can point out some features which might make it a little easier. So this really bright thing right here, this is, I believe that's the bottom of the spacecraft. So that's the antenna face. So let me go back to this rendering and I'll show you right there. Do you see how sort of like the brightest point of the spacecraft is on the bottom? And so that might not be what you'd expect. You'd expect the solar panel to be the brightest, but it turns out that the antenna face is actually the brightest, especially when the solar panel is in its vertical configuration. So yeah, so that's the bottom of the spacecraft. So that right in the middle of this is like the sun is basically perfectly bouncing off directly down into your camera. So like you're looking basically straight at a reflection of the sun. And then this other feature here, I believe that that's the solar panel, if I remember right, because as we fly around the spacecraft, the next thing we see is the solar panel. And then I believe that this is the front of the solar panel. So like this whole thing loops. So this whole thing could be mirrored. So as we go from x equals 0 to x equals 1, it could loop back over just fine. It's like going around in circles. And same thing with the vertical component here. This is a 0 sun angle, and this is like higher and higher sun angle, and at some point you end up at 360 degrees and it just loops back around. So this is basically two halves of the reflection of the solar panel. So again, you can see like the front of the solar panel and the back of the solar panel are quite reflective, but only if you're looking at the satellite from the front or the back. So that's just the final orbit configuration. This image we were just looking at, this lookup table, tells you how bright will the satellite be at a certain viewing angle, at a certain sun angle to the satellite. So that's pretty cool. And so there's a very straightforward encoding here between the camera angles and the spacecraft angles and where we are in that image. So I did a couple of those. This is for the final orbit of Starlink. This is the final orbit configuration with a visor sat. So this is with that shadow. Let me scroll back up. I'll show you what I mean. This is with the shadow implementation going on right here. Okay. Here we go. Okay, so this one right here is actually what would the reflection difference be. You can look at the difference between these two and see how much VisorSat makes an impact. I'm going to make this a little bit bigger so that you can actually see it because it's tiny. One moment. There we go. Oh boy. Okay, so this top one, if we look at the bottom face here, or yeah, I think this is the bottom face. Now I'm going back on myself, but you can see how basically part of the spacecraft gets a lot darker when the VisorSat is implemented. It's kind of cool. And then this is with orbit raise configuration. So this is with the satellite panel or the Starlink solar panel down instead of this one, down instead of up. So what do we see there? Well, we see that basically where the reflection happens for the solar panel is completely shifted around. So instead of being sort of mirrored on the right there, on the top and bottom for the solar panel, now it's mirrored left to right because, I mean, it's kind of confusing to immediately be able to say why it moves like that. But if you think it through and again, if you become a patron and get access to this Python notebook, and you can think it through and realize why that happens. Anyway, we've just crossed the hour mark, and my plan was to make this only about an hour long. So I'm going to speed up a little bit, and let me know if I'm going too fast. Yeah, cool. Okay, so that's how we do reflectance. So now all we need to do is ask each Starlink satellite, okay, where's the sun? And what's your angle to the sun? And then we need to ask, okay, where's the camera? And what's your angle to the camera? And then we just position ourselves somewhere in this lookup table, and we say, oh, well, we're right in the middle of this. We should be really bright. Or, oh, we're right in the middle of this. We should be completely invisible. Cool. Okay, so I'll show you just a little bit of the rest of this document. So this is, I believe, without reflectance. This is what a time-lapse, a 30-second long exposure would look like without reflectance modeling at all. And this is what it looks like with reflectance modeling. I believe that's, yes, it's a VisorSat. So the difference here is really quite substantial. Let me zoom out so you can see it a little bit better. I mean, VisorSat clearly is doing a lot, first of all, but also if we're just naively modeling these Starlink satellites, pretending that they're equally reflective from all directions, spherical cows as they call it in astronomy, it's completely inaccurate, basically. So adding in the reflectance really makes a massive difference. The key to making the reflectance work, though, is to hand calibrate the magnitudes. So this is sort of where things get a little bit fuzzy, but based on the best available data for the observed magnitudes of Starlink satellites in each of these conditions, I basically went into VerseView and I placed the camera in different viewing positions, and I calculated, okay, what is the magnitude of the satellite that's passing directly overhead right now? And is it the right number? And I just did that over and over, hand calibrating the reflectance model to the magnitudes that have been observed in real life. So we get these numbers. I'm not going to go super into the detail, but like you can go into that if you'd like. This document goes into plenty of the detail. And then like some other things so yeah, I think the rest of this is just sort of like extra detail, like how did I calculate the orbits and stuff like that. So feel free to become a patron and check this out in detail. I'll be releasing that probably end of this stream. So by adding in reflectance, I'll just show you hands-on. Let's turn to make sure reflectance is off. Okay, so reflectance is off, and I'm going to give them realistic. So we're going to use the final orbit Starlink magnitudes. I believe this is the non-VisorSat. Yeah, these are the non-VisorSat magnitudes. So let's check it out. And please let me know if you have any questions. I'm kind of just barreling on here and assuming that you're understanding what I'm saying. But if you're confused by anything, I'm watching the chat and ready to respond. Abraxas says, what kind of sucks is you need to learn concepts for a long time before you get to do cool things. There's so many things I'd love to do, but to get there, it requires months and years of learning. Yeah, I feel you. It is my favorite thing to learn new things, and the thing I'm probably most afraid of in the world is losing the energy to learn new things. Yeah. But I completely agree with you, and I think my best advice is try to get a job or try to find a career or a job which enables you to learn the things that you want to learn. I do video consulting for Veritasium and for other science YouTube channels, making visuals like these. And so, so basically, like, I get to do the thing that I wanted to learn more about. And all it really took is like going after it and doing it. Different people come from different places of privilege of being able to do that, but please feel free to, message me if you want to get into, visual making for science videos or science writing. I mean, science writing is a great job because you just basically get to learn things all the time. Anyways, here's the Earth. I'm going to turn the brightness up. It's going to get really overexposed. You can say, hey, it's India. Anybody watching from India? I know I have a lot of fans from India, which is great. But, okay, so here we go. Here's the Starlink satellite. So you notice, before I had them exaggeratedly bright, now because they're realistic, this is the pre-visor sat magnitudes, and they're showing the reflectances, I have to turn this way up until you can actually see some stars floating around, to actually see them. Okay, so that's pretty cool. If we fly around these satellites, you can kind of see, it's a little subtle because, it's just subtle, but like if I fly beneath them, their brightnesses do change. So I'm gonna go really wide angle here and slow the camera down so that you can get a better sense of it. I'm gonna turn the brightness down a little bit. But as I move around here, why don't I do a sort of a launch. So I'm gonna slowly fly up, and we can see how the reflectances change continuously. Welcome, Guiava. I hope I'm saying your name right. Please, if it's 2:30 a.m. in your country, please go get some sleep. No need to stay around. I'm going to be posting this later, so if you need to get some sleep, please do. Sleep is good for you, Watch Goodbye Night Sky episode 2 if you need further evidence of that. But yeah, so here we go. So we can see the reflectance. If you look closely, you can see the reflectances being affected. So as we change our camera angle here, and the brightnesses of the satellites are changing. Pretty interesting. Thank you, Guiava. That means a lot. That I'm one of the favorite channels on YouTube. That's a huge deal. I put a lot of work into these videos, so to be recognized like that, that's awesome. Thank you. Love you. Love you all. Thank you all for joining this. It's so fun to have you guys to talk to on this beautiful Saturday. But as we go along here, you can see okay, so here's a great position actually. So as these satellites on this particular train are coming towards us, you see that? They're darker over there. Even though they're in direct sunlight over there, they're darker over there. But as they get closer to us, they get brighter and brighter. And that's because we're kind of above them, so we're probably seeing the bottom or the top and the solar arrays bouncing off the sun. But over here, because the Starlink satellites are constantly pointing their antenna face down to the ground, that means that in this case, the solar panels are pointing away from us over here, because the satellites are kind of going like, phew, and by the time that they're over here, they're on the other side of the Earth, and the solar panel is pointing basically directly away from us, and we're looking at a side of the spacecraft which is not being illuminated. And so they're basically invisible. So this is a great position. Actually, I really like this shot. This is like gorgeous. I think I'm gonna like change the exposure here a little bit, and maybe I'll just make this the the thumbnail. Let's save this. I'm going to put it on my desktop. Thumbnail. Beautiful. Okay, great. Isn't that so cool? I'm so glad to share this with you. Okay, so that's how you do reflectance and extinction. So as they pass into their shadow, they're getting redder, which is extinction. As they move around and change their orientation with respect to the sun and the camera, they change their reflectance, which makes this already, I think, more accurate than any other visualization I've seen of this. Okay. Okay, goodbye, Jazim Maths and Physics. It's so great to see you in here. Susie, welcome, Susie. Are you modeling the current amount of satellites? Great question, Susie. So, basically, no. So this is the end of phase 1. So this isn't even 42,000 satellites. We're going to get to that in a second. But this is only, I believe it's 10,000 satellites. Oh, Jazim Maths and Physics, great. Please keep on if you can, but please go to sleep if you're tired, because this will be posted afterwards. So, but yeah, to Susie's point, this is, I think, I post, I believe I put it in here. Whenever it launches, it tells me, okay, this is 4,000. This is only 4,409 satellites. That's ridiculous. That is completely insane. I didn't quite realize that. But, you know, we fly away from here. Well, yeah, so also as you get farther away from the satellites, they get dimmer because you're getting farther away from an object which is reflecting. And so light goes as the square inverse law. So as we get closer, things get brighter. As we get farther, they get dimmer. Okay, so I can't really show you all of them at once. I mean, I guess I could go really far away and boost the exposure. There we go. But yeah, so that's only 4,400 satellites. That's insane. And then this isn't even showing the, 4,000 other satellites that are already in orbit. There are currently about 600 satellites in orbit that Starlink has put up, but I don't actually have that data set here, funny enough. I have it in the all satellites rendering, but that thing takes ages to render. So, very cool, very cool. Let's go to the next step. So, okay, there's VerseView Planetarium. Let's catch up. So we're at step 2, reflectance mapping. Step 3, magnitude calibration. I talked about that. Basically, what I did there is like I remember for some reason it was particularly advantageous to fly over the River Nile right here, and I put the camera directly on the ground, and you see that the Earth is rotating. Well, I had this button called Camera Parented. And so I can click Camera Parented, and now we're actually rotating with the Earth. So if I look at the horizon very closely, things get a bit blurry, but you can see that the stars are in fact moving. The stars aren't moving, we're moving, but we're moving with the Earth. So I went here and I calibrated. I said, okay, here's all the satellites. I made it in the PowerShell. I made it print out what the magnitude was of the closest satellite to me, and then I just did a trial and error loop of calibrating their magnitudes. Okay, so yeah, so that's kind of the simulation. I mean, there's not much more to it. I mean, let's go to 42,000 satellites though. So this is the grand reveal. It's taken me an hour and 14 minutes to get here, but hopefully this has been interesting the whole way around. Let's see. So we're going to turn this back on. And let's go to 42,000. Where is 40? Oh, yeah. So I'm going to change phase 1 to phase 3. Okay. Escape and boop. Let's see. I just realized I think I left reflectance on for that last thing I was just describing. So I think that the reason that those... I feel like an idiot, but the reason that those satellites were getting dimmer as they got farther away from us wasn't because of the solar panel, it was because of them getting farther away from us. So my bad. Let's actually look at what that looks like. Here we go. That's what I'm expecting. Hello, India. Hello, Egypt. Hello, Saudi Arabia. Okay, so let's find a nice camera angle here. Let me know if my camera movements are absolutely jarring. Okay, so and now this is a bit more realistic. So as I fly around, as I go below the satellites, all of a sudden we get a bunch of reflectances happening because the bottom of the satellites is the brightest part. If I go above the satellites, they basically all start to disappear because we've passed the threshold where the cameras now basically can't see them anymore. Okay, very cool, very cool. So there we go. So that's is this phase 3? Yeah, I just turned on phase 3. So this is 42,000 satellites with extinctions, reflectances, calibrated magnitudes. I also increased the dot size here so that you guys can actually see them, but normally they would not appear this large. Yeah, so one question that I got, which is a really great question, something that I wondered about as well, is these satellites are tiny compared to the Earth. Like, there's no way that we're going to be able to see them flying around, right? And that's a really valid question, but it turns out that both your eyes and cameras do this thing. They do this thing where as the light comes in, the light spreads out. And also, as a point source far out in space comes through the atmosphere, it kind of gets warped by the atmosphere. And so when it hits your eye, it actually ends up looking bigger than it is in real life. So it gives you a weird intuition. Like, you think that bright stars, I'm going to just change camera views real quick. You think that bright stars are actually larger because when you look at like Sirius or what's another bright star? Vega, I think? Sirius. Let's just take Sirius. It looks really big because it's brighter, but you think that it's actually big, but you're actually not seeing how big it is because it's so far away that you wouldn't see its angular diameter anyways with the naked eye. So these Starlink satellites, even though they're super tiny, the brighter they are, the larger they seem. It's something called a point spread function. And because we're not modeling that directly here in the simulation, let me switch over to here. But, you know, I basically calibrated it to what a camera can see. So, or what how bright the sources in cameras end up being. So there you go, point spread function. So check that out if you want more information about that. So anyway, what was I gonna do here? There's a weird blending thing that was going on here. One of the issues, maybe now's a good time to talk about limitations and issues, actually. One of the problems with this simulation is that it's very like handcrafted and things fail very quickly, very easily. So it takes a lot of time to develop. For instance, if we zoom in on some of these satellites, you can see that the point sprites, the little dots, are like overlapping with other ones, even when they're dark. So like right here, there's like black squares that are covering up other satellites, and that should not happen. And that's because for some other reason, I changed the blending function. So like, for instance, let's find that code. Oh boy, where is it? The blend function. GL blend. Here we go. So I have like a couple of blend functions which I turn on and off based on different use cases, based on different visualizations I want to make. So it's very loose. This is not like a very good game engine or like a very AAA like finished product. But let's see. Okay, that's definitely not what I want. They were just all black. In a second here, I want to go into questions. So let me know if you guys have any questions. Also, if you have any challenges, like what should we do with these satellites? Should we make like 40,000 times 2? Should we like see what it would take to crash my computer? That could be kind of fun. Okay, that was not working either. I don't know why, but I think that 1,1 is the proper blending function, and I don't know why I didn't have it set to that. Let's see if that one works. Yeah, so questions. And if there's no questions, that's cool too. We can just all go about our day, chilling. Okay, I think that's more like it. Yeah, so now they do sort of do a weird overlap thing, but at least they're not as weird. Also, when they're smaller, that overlap issue isn't as big of a deal. So anyway, should we make a cool camera move? Maybe? That could be kind of cool. At this point, I think this is the end of my presentation. Let me just make sure. Oh yeah, forgot about this. So pictures taken with cameras like these ones have a very specific gain and gamma curve. So let me turn up the gain. If I turn up the gain on this, whoops. If I turn up the gain on this image, it gets brighter and brighter and brighter. And that's just a simple multiplication. I see some questions coming in. Very exciting. I'll get to you in a second, Shockwave 3. As we turn up the gain, it just gets brighter and brighter, right? Obviously. This is a multiplication on the entire image, on how bright is everything in the image, times 2 or times 10, right? And things get really out of whack really fast and start to look terrible. But there's another control over brightness that we have. It's basically contrast. It's called gamma. So if I hold the control key and scroll, all of a sudden, now there's a lot higher contrast. And in fact, the easiest way to show this is to look at the Milky Way. Oh gosh, that looks awful. But if we look at the Milky Way, this is like really high contrast Milky Way. But as I turn that down, it gets really washed out and you start to see more and more stars. And that looks kind of nice, right? So changing the exposure, or the gain, and the gamma, in turn together change the exposure of the image. So what I did here was, and I don't really want to go into the code here because it was a complete mess, and you guys will hate me for it because it won't make any sense. But I took actual images from my camera. I pointed them at the exact same part of the sky, zoomed in, matched the camera to the image that the virtual camera to the camera that I actually took the picture with, and then I changed the gamma and gain curves until basically I did an optimization, an automatic programmatic algorithmic optimization that brought the two images as close together as possible, so that when I take a picture or take a screenshot in this program, it's actually the closest thing to what a real camera would actually take. This was a very long and drawn out process. I think it took me about 2 weeks. And it was kind of a massive waste of time at the end of the day, but it's really accurate. So now when we look at these simulations, I can really trust personally that I'm seeing ground truth, or at least the closest thing to ground truth that exists. So for a moment, let's change the time of day. I'm going to change it. Whoopsies, that button doesn't do anything. There we go. Let's make it nighttime in the USA. And let's fly over to California, where I happen to be filming this live stream. Actually, let's go to the Black Rock Desert. I believe the Black Rock... Oh, wait, I have a button for that. What am I doing? Go to Black Rock City. There we go. Now we're in Black Rock City. Welcome, everyone. The camera's upside down, which is very confusing. We can see the sun setting. I'm going to click Camera Parented so that we're rotating with the Earth. I see some questions coming in, one from Susie, which I'll get to in a moment. And yeah, so I literally, from the time lapses that I had previously taken in Black Rock Desert, I went and I matched the brightnesses of the stars to the brightnesses from time lapses taken with my camera. So when you look at a video like, let me go back, like this. When you look at a video like this, my rendering, and when you look at the corner and you read that it says all phases, atmospheric extinction, reflectance, etc., you know that this is probably the most accurate representation of what Starlink satellites will look like to a camera that exists on the internet. These are not animations, these are simulations. And that's all I got. So let me answer some questions now. Let's go to full screen here. Okay, great. I think I got a wicked sunburn. I don't know if you can tell that. I was hanging out outside today, and I think I've gone all lobster, so excuse that. Okay, first question. Are these the real-time locations of the satellites? Either way, it is so cool. Thank you very much to Shockwave 3. They are not the real-time locations. So, first of all, that many satellites has not been launched yet, right? So there are only 600 satellites. But this is what, in real time, 42,000 would look like. So let's get that. So if they end up launching what they've published to the FCC that they will launch, this, let's get that brightness up. This is what we'll actually kind of see, right? And this is in real time. So let's fly down to India, maybe rural India, so we have a nice night sky, and you can see. That's kind of the rate that they'll actually be moving in the sky. Some of them are at higher altitudes, and higher altitudes means that they're moving slower, and that they go into the Earth's shadow later. So some of these ones that you see all the way over. Oh, we're not on classic. I'm sorry about that. This is how they're actually moving in real time. So. Some of the satellites over here on the left, these are those higher altitude satellites, and the ones that kind of fall into the Earth's shadow sooner are lower altitude. And you can see that by the way that they move. I mean, these ones on the left are moving much, much slower than the ones over here. So this is what it looks like in real time. Okay. Yeah, sorry about face cam. It's classic mistake. Okay, so from Susie, are all these satellites going to make launching spaceships and finding good launch windows so much harder? Yeah, that's actually an excellent question. Funny enough, that's a good question for Tim Dodd, the everyday astronaut. We talked about that a little bit in our interview, which all the interviews are available for patrons on Patreon. So if you want to give some amount of money every month to the channel, that would be hugely appreciated. It's not necessary, but if you have a little spare cash, I mean, it would be supporting the future of the channel, and you would be able to get access to all of the interviews full length. I'm going to post the Melvin John one, Melvin John Ashews interview today, I think. Anyways, so so Tim talked about that in the interview. He said that he was talking to Peter Beck at Rocket Lab, which is a New Zealand rocket launch company, and they have this thing where they had this situation come up where they were trying to get launch windows for their payload customer, and they realized that there were so many Starlinks now that they had to like thread the needle a little bit more. So it is going to make, at least it's already making life harder for Rocket Lab, and I imagine it's making life harder for SpaceX too. The good thing is that tracking for these satellites is really solid. So like we know exactly where they are. There's frequent reports of them. So like their orbital parameters are very well known. And every single Starlink antenna on the ground can tell SpaceX, hey, I just connected to a satellite and it's exactly in this location. So that'll help even more with tracking and stuff. So if we know where they are very specifically, it shouldn't be too big of a deal. One thing I worry about is something called Kessler syndrome. And Kessler syndrome is where the satellites basically, if one satellite hits another, let's say we have 42,000 satellites and 2 of them go rogue, or one of them goes rogue and loses contact and starts firing its thruster for no reason. If it smashes into another satellite, that's not a good situation because there are so many satellites and that debris is going to go flying out in every direction, like the movie Gravity. And those shards are going to destroy other satellites. And then those satellites are going to go rogue and destroy other satellites. And basically you just have like a night sky and not just a night sky, you have a orbital sphere of trash, and not just trash, but like really high speed, dangerous, sharp debris that if you're trying to go to Mars is not going to be a very happy thing. It's like, oh man, here we go. launching up to Mars, and there's a tiny piece of a Starlink satellite just like rips through the hull of your spacecraft during launch and depressurizes the whole thing, and everybody dies or something, right? Like this is clearly something that SpaceX has to think about because of their goal of sending humanity to Mars. So my sense is they're thinking hard about it, but I don't really know what's being done. I haven't heard anything about what's being done. So from Dimitri, my man, welcome. Dimitri is a patron, very valued patron, might potentially be bringing Russian subtitles to the channel, which would be awesome. No pressure, by the way, Dimitri. But I see your question, does this matching of photo and simulation work in all directions? Like if you make a photo in daylight and point it more towards or from the direction of the sun, optimal ISO, exposure, etc. will change. This is an excellent question. My simulations are, the calibration to camera is only for basically a single case, which is darkest night, no light pollution, and a very specific field of view, a very specific ISO, very specific aperture. So it's sort of like if you were taking these time lapses with my exact camera, this is what it would look like. And my exact camera isn't even like the best. So that's kind of why I felt okay calibrating to it, because other people will have better cameras, like more sensitive ISOs and stuff. And yeah, and basically they'll see a lot more streaks. But I wanted to play to the sort of like, play to the crowd of, this isn't a problem at all, right? Well, okay, even if you're using a terrible camera like the one I have, I mean, it's not terrible, but it's okay. It's reasonable. Like, we're still going to end up with problems, right? Even if you don't have the most sensitive equipment, you can still see them, and they're still a huge issue. Yeah, so that kind of answers that question. One thing I forgot to show you guys is the simulated long exposure mode. So I'm going to make this really dim, and then I'm going to open the shutter. So camera shutter, open. And now, every single frame, instead of clearing the screen, it's adding up every single new frame to the last one. So basically, it's like a simulated long exposure. And so this is how I did the simulated star streaks, is I literally let it run in real time for an entire night, and then it spat out, like thousands of frames as a real-time sort of time lapse. So that is ridiculous. I should mention these are not visor sat magnitudes. These are OG Starlink magnitudes. Maybe I should quickly swap to the visor sat ones, just so we're looking at the most accurate visualization. I saw another question come in, and I will check it out in 1 second. Let's put it in final orbit mode. Okay. Do you think OneWeb and Amazon mega constellations with Starlink will have a noticeable effect to the night sky once completed? Andrew, that is an excellent question. Let me think about my full answer to that. I mean, to the night sky, no. And let me show you what I mean by that. Let's bring the exposure up a bit. There we see some Starlinks. Let's go somewhere where there's like no light pollution, like in the middle of the ocean. I would love to go stargazing in the middle of the ocean. That would be really cool. Okay, so here we are. We're not quite on the ground, but we're close enough. And let me turn up the exposure a bit. Now, the human eye does not see this. If you're going to take a trip to the middle of the ocean, oh, I'm below the Earth now, there we go, and look at the night sky, basically time lapses lied to you, because they take in much more light than your eye can actually take in, and that your eye is sensitive to. The eye is an amazing thing, but it can probably only see about something like this. And I don't even know if you can see that on the stream. Like, it's so pathetic, kind of. Maybe more like that if you have really good eyes, or if you have a telescope. Maybe more like this. So sort of more and more stars, the more light you can gather. With a human eye, again, you're not going to be able to see the Starlink satellites. They're magnitude 7, magnitude 8. The goal for the astronomers to get constellations is to get their magnitudes to magnitude 9. If you're not sure what I mean by magnitudes, go check out the main video, because I go into pretty good detail about it there. But because they're magnitude 8 or 9, like, it's not going to be a big deal for astronomy. It's not going to be a big deal for the human eye, for amateur astronomy. It is going to be a big deal for telescopes, like mega telescopes, even amateur telescopes, like people who do asteroid hunting. They're going to have a lot of issues with this. Not because they can't throw out exposures, but because every single exposure for a huge portion of the year, every single exposure will have a streak in it, basically, or every other exposure. So, like, you won't be able to look in a whole half of the sky. Let me show you what I mean. Let's go to the Vera Rubin Observatory location. Oh boy. So right now, at the time that I currently selected, it is daytime. It is daytime at the location of the Vera Rubin Observatory, and so we need to make it go to sunset. There's sunset. Let's do this a little smoother. I'm gonna change the minutes. There we go. So there goes our simulated sunset, which is quite cool. Okay, so then now we have full sunset. Let's brighten things up a bit so that we can start to see some dusk going on. And so here, like we can see some Starlink satellites, right? But you wouldn't be able to see this much of the sky this late into the evening. Let's change this even more. Skip forward, skip forward, skip forward. Let's get to the middle of the night. There we go. So now the sun is just kind of over there on the horizon, right? But yeah, so like, I think, yeah, the month that I've set here is June 20th. So that's the winter in the southern hemisphere. Let's change this to be the summer in the southern hemisphere, which is in December. So here's December. We got to change the time of day. Here we go. Oh boy. So in these sort of middle latitudes, northern latitudes, but particularly like where a lot of telescopes are near the equator or in the southern hemisphere, but like mostly near the equator, you're going to be able to see Starlink satellites the entire night long. And like an entire swath of the night sky is going to be ruled out because you can't take long exposures in that area. So that's kind of my answer to that question. The short answer is, do I think that they'll have an effect to the night sky when they're completed? Basically, no. If OneWeb and Amazon and Facebook's constellation and maybe Russia's constellation or maybe China's constellation or Samsung in South Korea was thinking of making one, if they just decide like, hey, screw astronomers, like let's just put up a bunch of satellites, like then we're going to have issues because they don't have any regulations that they're forced to say, okay, let's keep them under magnitude 7 or magnitude 8. They can just basically do whatever they want, which is kind of nerve-wracking because companies don't always do the best thing. And neither do countries. But yeah, so that's kind of my answer to the question. They won't have an effect to the night sky if companies and countries and people who put up these satellite constellations are reasonable, if they're considerate. But if they're inconsiderate, if they just go for it and they don't ask anybody and they don't respond to pokes and prods to keep their satellites dim, we might end up with a night sky that's filled with these things. Twilight streakers that saturate digital sensors and cause all kinds of havoc. The biggest thing I think I worry about, to answer your question sort of tangentially, is the asteroid impact stuff. Because, this area of the sky, looking towards the sun, for half the year, you're not going to be able to look even directly near the sun in the summer for a lot of these observatories which do the asteroid hunting. So Pan-STARRS, the Palomar Observatory, There's, I believe, some of them on Paranel, the Paranel Observatory, I think does asteroids as well. But I remember Pan-STARRS being the largest survey of asteroids, and like they're gonna have big issues, man. So that's kind of my answer to that question. I'm gonna come back to full screen, full camera view here. Any other questions? I'm gonna stay on for a minute or two here, and otherwise, if this is kind of the end, so if there's any more questions, feel free to ask them. But that's kind of it. This has been a fun stream. I hope that this makes sense to you. If you're curious to learn more, feel free to go become a patron, and you can read that write-up that I'm going to post. If you want to use VerseView, let me know. Does it post in the chat if you want to use VerseView at all? One thing I wanted to show you is that VerseView isn't just rendering of VerseView doesn't just render the solar system. It can also do other things. I just don't know if enough people want to use it that would justify me like making it easier to use, because right now it's a huge pain. Kind of like Manem, the Grant Sanderson's code. So here's a rotating cube. Very interesting, right? Who cares, right? This is my test code. So I also built this graphical user interface to do camera positions and stuff, so you can do those cool camera movements we were talking about. So like, for instance, let's keyframe our rotation and position of the camera. And then I'm going to move forward like 1 second, and we'll fly away. There we go. Create another keyframe. And then I can change the interpolation of the position and rotation here. This is all built in Python too, so this is all quite extensible. So then where we can see the camera moves away. So like, this is something which for some reason doesn't exist in the Python world. It is kind of like dependent on a lot of fringe dependencies like custom code and stuff, but I'd love to share it with people if there's a demand for that. Anyhow, I haven't seen any other questions come in, so I'm going to assume that that's the end. I want to thank you all for watching, so much for joining. This has been a super fun time. Thank you for your questions. If you have any more, feel free to ask them in the comments of the post. I'll post this video. And yeah, hope you have a great day. If you know anybody at Starlink or at OneWeb or Amazon, send them the video. Tell them to watch their backs, because we're watching them. We're counting their satellites. We're watching their magnitudes. Thank you, Susie. Thank you very much. That simulated sunset's really cool, right? There's a video coming actually about that. About what happens if you take a picture of the sun at the same time every single day, not including or not accounting for daylight savings time. Think about that. Where would the sun's position go? Anyway, I'll be using that for that video, which I'm excited to show. So thank you. From Loginork, amazing stream, was nice to watch when programming by myself. Keep up your own work. Greetings from Poland. That is so cool. Thank you for watching, and hope you have a great day there. Okay, calling it. Have a great